So this lesson is about applications of definite integrals, and we'll talk also about the total change interpretation of a definite integral. So the first thing to think about, and you probably have a sense of this already given the examples we've done in the previous two lecture modules, that if you have a function which is a rate of change, like velocity was a rate of change, then the definite integral from a to b of that function is essentially the total change in the quantity. So if velocity is a rate of change of distance, the integral of velocity is the total change in distance. So a couple things before we jump into some examples. A little bit more information about the definite integral symbol and what some of the notation means. So if you look at the definite integral symbol and you want to think about what the units for that are going to be, if f is a rate of change, for example feet per second, this dt essentially represents a small bit of the variable t, which is time, so times a small bit of time. So the units for the integral, which essentially add up the area under the curve, or the rectangles in the right-hand sum, the units are going to be the units of f of t times the units of t. So in our previous examples, with velocity, which were feet per second, times time, which were seconds, we ended up getting feet, because the seconds canceled, and that gave us distance. So I did mention that that little dt is a technical piece of the notation, and what it represents is the small bit of time, or you can think of the width of those small rectangles that we used in estimating definite integrals as areas in the right-hand sum and left-hand sum. And then a little bit about the symbol, that elongated, it looks like an elongated S, and it's to make you think sum, because what we did when we estimated was we computed f of some, f of 20 times the dt, which was 2, and then we did this a whole bunch of times for different rectangles, and we added those all up. So the integral became essentially a sum of values of the function, those are the heights of the rectangles, times these little elements dt, and those were the bases of the rectangles. Okay, so total change is an important concept, and it's going to underlie all the examples that we do in this section. So let's start out with something easy. If you know you've got a function c of t that represents the rate in kilocalories per hour at which you're burning calories at the hour t, and t is just going to be measured in hours after midnight, let's interpret the integral below. Well, again, think through units. If c of t is kilocalories per hour, and the little bit of the variable t is a variable for time, times hours, that suggests that we should get kilocalories, and that's exactly what the previous slide was saying, that if you're integrating a rate of change, you get the total change of the quantity. So total change in kilocalories over the time period, over time 0 to 24. So you might have burned 2,000 calories in that 24-hour time period. And integrating the rate at which you burn calories will help you figure that out. All right, so that's just a straightforward application of the definition of integrating a rate of change in terms of total change, but let's do something a little more complicated. So in this next example, we've got a bacteria colony, and we know that initially it's got a population of 14 million bacteria. So suppose that t hours later the population is growing at a rate of f of t equals 2 to the t million bacteria per hour. So first, let's write down a definite integral representing the total change in the population from time 0 to time t, or time t equal 2. So that total change, well, the integral from 0 to 2 of the rate of change, and we know that's 2 to the t, times dt, the little variable there, should give us the total change in the population. That's the definition. Total change of population from time 0 to time 2. So that's pretty simple. We just write that down. So now I'm asking, can we find the population of the entire colony at time t equals 2? Well, it's a little more complicated. I know that from time 0 to time 2, that my population changed, or essentially grew, by whatever this integral is. We haven't estimated that yet. But how do I find the total population? That's actually pretty simple. I just need to add whatever this amount is to the original population, or the initial population. So the initial population of bacteria we're given in the problem. It's 14 million. So the answer to this question is we're going to have the total population, so population at time 2 is going to equal initial population plus change in population. When the initial population, the problem says, is 14 million, and the change in population is the integral from 0 to 2 of the function 2 to the t dt. And so there are a lot of questions about what do you do with this. Well, we know a lot of ways to estimate that. We could graph that and do some estimate with area under a curve. That would be not too hard. Shortly, you're going to be able to look at a lecture about how to compute these exactly in R. We'll also have some techniques later that might let you compute some of these by hand. But so let me just tell you now that I computed this in R, and I got something like 4.328 million as an estimate for that integral. And if we add those together, we get 18.328 million bacteria at time 2. Okay, so that wasn't too bad. We're getting into a slightly more difficult example, and this is actually using a graph you've seen before. But here's a problem where we want to talk about a car traveling with velocity 55 feet per second at time 0, so we know a little something about our initial velocity. And then I'm going to give you a picture of the car's acceleration, and we haven't talked a lot about that, but here acceleration in this situation is feet per second squared. That's how much you're speeding up or slowing down, and this axis is t, and that's measured in seconds. So the graph here is acceleration, and we're going to ask a couple of questions about total change. And I'm going to ask them in a way that might not seem obvious. So think about the first question. Is the velocity of the car increasing at t equal 2 seconds? Well, let's just think practically. Where's t equal 2 seconds, first of all? It looks like it's probably right about here. So what do I know? I know that the acceleration is 15 feet per second squared. So that means I'm actually accelerating, and that does mean my velocity is increasing. That's what acceleration means. If you have a positive acceleration, so positive acceleration really in normal English means you're speeding up. Okay, so at t equal 2 seconds, we have a positive acceleration. So is the velocity of the car increasing at t equal 2 seconds? Yes, not too tough. Okay. So the second part of the question, at what time in the interval from t equals 0 to t equal 18, and again, this is t, and this is acceleration of t, and units are always helpful, feet per second squared, seconds. At what time is the velocity of the car 55 feet per second? So this takes a little more work. So what do we know? We know velocity at time 0 is 55 feet per second. Okay. And we know that the acceleration is a rate of change of velocity. And think about that, because velocity is feet per second, and if you think about how that changes per second, that's feet per second squared. That's acceleration. So what's the total change in velocity? that should be an integral of acceleration. So the total change in velocity, let's say from t equal 0 to 6, would give us that. So if you think about what's going on in this picture, if we know that the car starts out traveling 55 feet per second, and for this entire time the car is speeding up, it's got positive acceleration. So you're adding some total change. What's the total change? You'd have to compute that area, and we've actually done that in a previous lecture section. But then what happens down here? Perhaps for this bit of the graph, the car starts slowing down. Negative acceleration means deceleration. You start slowing down. So if these two areas are the same, we'd speed up to some higher velocity and then slow back down to our original velocity. So it looks like at time 12 we should be going 55 feet per second again, because we started out going 55 feet per second. So that's just a little bit of looking at the graph and trying to understand this total change and rate of change idea. Okay, third part of the question. During the interval from time 0 to 18, what's the car's maximum velocity, and when does it occur? So this is actually a really interesting question, and if you again think about this in kind of standard, so this is in seconds, t is in seconds, standard terms, we start out traveling at 55 feet per second, so your velocity at time 0 is 55 feet per second. Your acceleration is 15 feet per second squared. It's less here, but your acceleration is still positive. You're still speeding up for this whole time. And how much do you speed up? What is your velocity at time 6? Well, it should be your original velocity plus your change in velocity. And that's just the area under the acceleration curve. We've done that before. And I think we came to the conclusion that that was 60 in a previous example. So we get 115 feet per second. Now if you think about what happens after time 6, you're decelerating, you're slowing down, slowing down, slowing down. You're actually slowing down quite a bit. So the maximum velocity in this picture is going to be right at time 6. You do speed up a little bit after time 16, but you can check that out. It's not gonna get you back to where you were. The maximum velocity occurs at time 6, and you're going 115 feet per second. Okay, one last bit. At what time is the car's velocity equal to 0? So this might be a slight trick question, but let's think about that. We know that our velocity at time 0 is 55 feet per second. That's given. We also computed the velocity at time 6 just on the previous slide, and that was essentially the 55 plus the integral from 0 to 6 of the acceleration. So the total change basically in acceleration is total change in velocity. So that was a 55 plus a 60. And now think about, well, when could you have the lowest velocity? If this tells you you're decelerating, let's think about what the velocity at time 16 would be. Well, it's going to be the velocity at time 6 plus the integral from 6 to 16. The area, which will now contribute negatively, and that's going to be 115 plus, and we'll get a negative in here. And if you just think about that guy right there, I think we get a negative 30 for that. This is going to be a 4 times a 15. That's a 60, and since it's below the axis, you get a negative. And that's a triangle that has base 2 and height 15, so that's another 15 negative. So it looks like 150. Oh, 105. Looks like 105. So it looks like we're only going 10 feet per second at our slowest point, which would be right there. So this is sort of a trick question. The car's velocity is never equal to 0. You almost get there, but you don't quite. Okay, so I'd like you to reflect and ask yourself if you can set up a different definite integral to model a total change problem, and then use definite integrals to solve different applied problems. If you want more practice on this, you can look through section 5.4 in your textbook, and there are lots of applied problems. Okay, thanks for listening.